Hi, and welcome to our discussion of atmospheric dynamics. This is the third video on mass continuity and the mass continuity equation. In our last video, we talked about the mass continuity equation, and we looked at how we can determine vertical motions from the changes in convergence and divergence throughout the depth of the atmosphere. This method for figuring out vertical motions is called the kinematic method. Of course, we talked about kinematics and the kinematic properties. One of the kinematic properties is divergence. And since this mass continuity equation is based mainly on divergence, it produces or tells you what your vertical motions are as a result of convergence and divergence in the atmosphere. So that's very important. You should know that this is one of the methods for figuring out vertical motions. It's the kinematic method. So in our atmosphere, you'll find convergence and divergence in many different places. And as we mentioned, it causes rising sinking motions. Convergence and divergence is found near fronts and troughs and jet streams and boundaries, and everywhere just about you'll find convergence and divergence. In the lower atmosphere, the convergence and divergence is mostly a result of friction. Friction of the wind causes cross-isobar flow. You guys have seen that on weather maps where the wind is going across the isobars. And when the wind is going in across the isobars, it causes convergence. When it's going out across the isobars, that causes divergence. So down the lowest layers of the atmosphere, you can actually see the convergence and divergence very well. And actually, if you can see it, you can probably calculate it. So there are many different computer methods for calculating convergence and divergence in the lowest layers of the atmosphere. Sometimes we take the convergence and divergence and multiply it by other properties, such as moisture, and then we'll figure out where moisture convergence is. This is one method for forecasting thunderstorms, looking at where most of the moisture is pooling up or where it's converging. In the upper levels, you get convergence and divergence as a result of acceleration and also cross-contour flow and near the jet stream levels. But in the middle of the atmosphere, we have some problems, and we've talked about this already. We alluded to this. We looked at the divergence equation for natural coordinates, and we said that speed divergence is offset by directional convergence in the middle of the atmosphere, and likewise speed convergence is offset by directional divergence. So they offset each other. That's the problem. When the isobars or the contours are coming together, that is directional convergence, but the speed will increase, and that's speed divergence, or vice versa. If you see the contours or isobars spreading apart, you know that the wind will slow down. That's speed convergence. But of course, the spreading out of the isobars means that you have directional divergence. So you've got the difference between two large numbers, and typically that produces a very small number. And that small number, it's hard to decide whether or figure out whether that is a positive number or a negative number, whether it's convergence or divergence overall. And the problem with that is, of course, our instruments have some errors. We measure most of the winds in the upper atmosphere using radiosondes. And if we have small errors in our measurements of wind speed and or wind direction, then that'll cause errors in our calculations of speed convergence or divergence and directional convergence and divergence. So since we're taking the difference between two large numbers, we get a small number. And that difference is going to be small and prone to error. So we have some issues with measuring divergence in the upper levels of the atmosphere. So instead of measuring divergence and calculating divergence, which is prone to error, we have to look at another way of figuring out if there's convergence or divergence in the upper atmosphere. Before we do that, I just want to mention that looking at directional divergence, remember that divergence is a result of speed and direction. If we only look at the direction changes, then we can then classify the convergence and divergence as either being difluent or confluent. By definition, Diffluence is the rate at which adjacent flow diverges along an axis normal to the flow at the point in question. Well, that's a definition. When you look at it, you can actually see the winds spreading apart. When they do that, that's diffluence. In other words, diffluence is only the change in direction. And if it is diverging, then we say that it is directional. We have directional divergence, and that's diffluent. Remember, though, that diffluence is often offset by convergence in speed. Correspondingly, you can also have air coming together in direction. We call that confluence. There's the technical definition, rate at which adjacent flow is converging along an axis oriented normal to the flow at the point in question. But basically, it's air coming together. Now, that's only directional convergence, but it has nothing to do with speed. And the reason I bring this point up is a lot of times you look at the upper levels of the atmosphere. Now, the reason I bring this up is because a lot of times in the upper levels of the atmosphere, you see confluent or diffluent flow. In other words, you can see a directional convergence or a directional divergence. A lot of times meteorologists look at that and say, oh, there's divergence up there. You can see the air spreading out. But those meteorologists are not necessarily looking at divergence. They're looking at only confluence or diffluence. In other words, the spreading out or the coming together of the wind. Remember that divergence is a result of two things. So whenever you see confluence, it doesn't necessarily mean there's convergence. And when you see diffluence, it doesn't necessarily mean that there's divergence. Remember, confluence and diffluence deals with directional divergence. And you have to account for speed also. As I said before, normally when we have air spreading out, it slows down. Diffluence in direction means convergence in speed, and vice versa. So don't just assume because the air is spreading out at altitude that you have divergence. It's not the case in the middle of the atmosphere. Another thing I want to mention that's really important is that the geostrophic wind is non-divergent. What does that mean? Well, it's what we just stated in the last slide and in the previous slides, that when the wind is diffluent, when it's spreading out, it slows down and you have convergence. So, in other words, the diverging wind is usually, or the diffluent wind is usually offset by confluence in speed. So, if the air is close to geostrophic, as the isobars spread out, it'll slow down. And that's our concept of a geostrophic wind. The geostrophic wind flows parallel to the contours, doesn't flow across the contours. And the geostrophic wind speed is a function of the gradient, the height gradient. So you really can't use the geostrophic wind to figure out if the wind or if the air is convergent and divergent. So, as I mentioned, directional divergence is compensated by speed convergence, and you can see that in all the weather charts. The flow follows the contours. This is just reiterating what we talked about before. So, in the middle of the atmosphere, where you do have this balance between directional convergence and speed divergence, in the middle of the atmosphere, we call that level the level of non-divergence. This is where there is really no convergence or divergence. The level of non-divergence is typically the level that kind of separates the upper level systems from lower level systems. Down low you have convergence and divergence caused by highs and low pressure systems. Aloft you have more or less open waves. And those open waves also create convergence and divergence in the upper atmosphere, way up high, near the jet stream level, because the jet streams cause acceleration and deceleration, which is causes convergence and divergence. So the level of non-divergence is the middle of the atmosphere. Typically, we assume it to be about 500 millibars. Above that, you have convergence and divergence near the tropopause and the jet streams. Down below it, you've got convergence and divergence near the surface because of frictional effects. So if you want to be able to calculate vertical motions, you need to be able to figure out the ageostrophic component of the wind, because the ageostrophic component of the wind is what causes all of the convergence and all of the divergence in the atmosphere, and as a result, that produces those rising and sinking motions. Well, that's all I have for the mass continuity equation. We'll continue on with this discussion when we get to vorticity and also jet streams.